Okay, we are recording. Hello, everyone. Welcome to our morning sessions of the Granular Material Day of our 14th workshop in mathematics at the University of Brasilia. It is a great pleasure to have you all here. We are starting our morning session with the talk of Gengchao Yang from the Sun Yat-sen University at Shenzhen, China. Gengchao, can you please share your screen?
Yes. Can you see the screen?
It's coming. Yes, we can all see your screen.
Okay.
Okay, so, go ahead. You have half an hour.
Yeah, can you hear me clearly?
Yes, clearly. Perfect. Yes.
Okay. So, hello, everyone. So before the talk, actually, I would like to thank the organizer, in particular, Professor Yuri, who actually invited me to attend this very interesting and also very relevant workshop. And also Professor Yuri actually guided my research work since the very first year of my PhD research. So big thanks to you. And I also would like to thank my supervisor, Dr. Fiona Ko. I think she's also here from the University of Hong Kong. And also my senior Jing Lu, who is actually going to give a talk later on about particle segregation. So my name is Gengchao Yang. Now I'm working as an assistant professor at the Sun Yat-sen University. The title of my talk today is Towards Multiscale Lattice Boltzmann Modeling of Granular Flows. So the problem is granular flow. I believe everyone here knows better than me that granular flow is a ubiquitous phenomenon in nature. So we can have this complex evolution of the sand dunes and also a lot of problems that has been mentioned by the keynote speaker today. And also we can have the collapse of our bag of cereals in our daily life. And in geotechnical engineering, we also have these landslide problems, which are large-scale granular flows and often cause huge economic loss and life fatality. And believe it or not, we from the pictures we take from the Mars, there are also some traces about landslides. So it can be a headache to Elon Musk if he wants to move to the Mars in the near future. So later in the following, I am going to talk about three different problems we have been working on. And all of these three different problems are about the granular flows, and we try to solve them using different strategies. The first problem I will talk about is about the sediment transport in a turbulent environment. So we know that the solid particles can travel in river in different ways. They can be dissolved in water and result in dissolved load. For some small and light particles, they can suspend in the main body of the river and result in suspended load. While for some large and heavier particles, they tend to settle to the bottom and roll and slide near the bed and result in bed load. So in this problem, we focus on the feedback between the suspended load. Let me get my pointer. The suspended load and the rough riverbed. So to this study this problem, we decided to do numerical simulations. And we know that we can classify different techniques for fluid flow simulations according to the time scale and the length scale. For example, if we want to simulate a water droplet, and we know that this water droplet actually contains a lot of water molecules, H2O, and then we can track the movement of each individual molecule and the interaction among them. And this kind of method is called, we can call them microscale simulations. And one typical example is the molecular dynamics method. And at the other end of the spectrum, we treat the fluid as the continuum, and we can solve conservation equations of macroscopic variables like the fluid velocity, the pressure, and also the density, for example. And this kind of method is called the macroscale simulations. And one typical example is the conventional computational fluid dynamics CFD. So the method we use to simulate the fluid flow is the Lattice Boltzmann method. So this method sits somewhere in between. So in LBM, we have this concept of fluid particles, which are statistical representations of a bunch of fluid molecules. And these fluid particles can actually interact with each other and stream on move on a prescribed regular lattice. And this method can be called a mesoscale simulation. So we use the LBM to simulate an open channel flow, and you can see that we have a bathroom placed at the bottom of the channel, and you can also see that we have a recirculation region between the peaks of the bathrooms. So this setup is actually borrowed from experiment. And actually in the experiment, they try to measure the velocity profiles for different positions using the laser Doppler velocimetry. And this animation shows a section of the three-dimensional lattice Boltzmann simulation. So this section is from the streamwise direction and bed normal direction. So we can validate our LBM simulations by comparing the numerical results to the experimental measurements. And you can see that both the first order velocity and the second order turbulence intensity and the shear stress, they agree with the experimental data very well. So after the validation, we can use the numerical data to calculate the total suspended load. So how to do that? So first, we have to calculate the sediment concentration based on this simple advection diffusion equation. But to solve this, we have to know what is epsilon s, which is the diffusivity for the sediments. And here we just do a simple assumption that this epsilon s is linearly correlated to the diffusivity of the fluid momentum, which can be calculated from the fluid quantities. So once we solve C, which is the sediment concentration, we can multiply that by the velocity distribution and do an integration along the depth direction, then we can get the total suspended load. So what we find is when the turbulence intensity is weak and the settling velocity is large, then we will get smaller total suspended load. But when the turbulent intensity increases and the settling velocity decreases, then the total suspended load will also increase. So in numerical simulations, we can easily change the geometry of the bathroom so that we can get different roughnesses. And what we can see is when the bathroom roughness increases, the total suspended load will also increase. So from this data, we can establish a linear relationship between the regularized total suspended load and the roughness factor, which can be very useful to estimate the total suspended load in engineering practice. So this is the our first problem. So in this problem, we didn't solve simulate the sediment explicitly. So this kind of approach can be oversimplified if the interparticle interactions and the interaction between the solid particles and the interstitial fluid becomes significant. For example, our second problem, which is about immersed granular flows. So one background could be the submarine landslide. So this work is inspired by an experiment carried out by Rondon and his co-workers. So what they do is they build two granular columns using the same glass beads, but these two columns have two different packing densities. So one column is denser than the other. And this column is first held by this metal gate, and they can really get rid of metal gate fast and release the water column. And what they find is the dense granular column collapse is associated with the slow dynamics and short run distance, while the loose granular column collapse has a faster dynamics and a longer run distance. the interesting thing is they also install a pressure gauge just underneath the granular column. And what they find is they measure positive excess pore fluid pressure in the loose case, while negative excess pore fluid pressure in the dense case. So related to this interesting phenomenon, the question we want to answer is how to quantify the influence of the packing density on the mobility of immersed granular flows. So to study this, we also decided to do numerical simulations. And this time we have to couple our fluid solver to a particle solver. And in this case, we use the discrete element method, DEM. So DEM actually can update the particle kinematics according to the Newton's second law of motion, and it can solve the interparticle interaction based on some prescribed contact models. And in this case, we use the simplified Hertz contact model. In our research group, actually, we couple a fluid solver to DEM in two different ways. First, if the CFD method is used, then you can see on the left that a fluid cell is bigger than a particle size. And in this case, we can calculate an additional interaction force between the particles and the fluid based on the solid coverage ratio and also the relative velocity between the solid particle and the fluid based on some semi-empirical drag models. If the lattice Boltzmann method is used, and you can see that the fluid cell becomes smaller than a particle size. And in this case, we can fully resolve the fluid particle interactions. And in the end, we not only got a fluid hydrodynamic drag force, and also we get a hydrodynamic torque. And from the experiments carried out by Rondon, we know that the excess pore fluid pressure can play a very important role in this particular problem. That's why we decided to use the LBM-DEM method to simulate immersed granular column collapses with different packing densities. And here you can see the collapse of a dense column and the loose column. And you can see that the dense column collapses slower and the run distance is shorter, while in the loose case, the collapse is faster and the run distance is longer. So if we look closer to the loose case, we can see that the lift up of the granular front during the collapse, which is also observed in some experiments. So the reason why this can happen is because the granular particles, they move too fast so that there is not enough time for the particles to displace the fluid in front. And as a result, the granular front get lifted up and there is a thin layer of pressurized fluid get trapped in between the fast moving granular front and the static rough base. And as a result, the friction is reduced significantly and the mobility can increase. So this is the phenomenon we often see in our daily life as well. For example, if you drive in raining day, then it becomes much easier to sleep and to lose control of our car. And this phenomenon actually we often call it hydroplaning, which can be characterized by a dimensionless densimetric forward number. So for the immersed granular column collapse, we can also try to calculate this densimetric forward number, and we plot this FRD against the packing density. And here you can also see different symbols, which is represent for different different column sizes. And what we can see is when the densimetric forward number is below 0.3, then there is no hydroplaning. While if the densimetric forward number is above 0.4, then hydroplaning becomes very significant. While if this number is between 0.3 and 0.4, we get some transition regime. So up to now, we know that hydroplaning plays a very important role in immersed granular column collapse. And this degree of hydroplaning can be quantified by this dense matter flow number. Then our question is whether we can correlate the runout distance with the dense matter flow number. And this is what we find. And the dots here represent the LBM-DEM simulations. And if we plot the data in a log-log scale, then we got this linear relationship. We can also try to add the lab data as well as the field data. And you can see that all this data, they fall into the same line. That means this relationship holds no matter the scale is. So it is still valid for a small scale problem and also for a large scale problem. So this is our second problem. But in this second problem, we try to solve the particle motion and the fluid motion separately, and then we try to couple them together. However, there is a very big flaw about this technique. That is the high computational cost. So maybe if we try to simulate the laboratory scale granular column collapse, it still works. However, if we want to simulate large scale geophysical flows, for example, on problem number 3, it normally contains millions of particles, then the calculation simply becomes impossible. So what can we do? So we need to take a step back and do continuum simulations, right? So currently that's the only approach. So actually in literature, many people have adopted various continuum approaches to simulate granular flows. So we have Lagree and his co-workers using the conventional computational fluid dynamics plus the VOF solver to track the dynamic evolution of the free surface to simulate this granular column collapse problem. We also have some people using the finite element method to simulate a chute flow with the lateral walls. So this is the velocity profile and this is the depth profile. And more recently, we also have someone using the material point method and the smooth particle hydrodynamics method to simulate granular column collapses. Also, these methods are more optimized for large deformation problems. However, even with this continuum method, a fully 3D simulation is still very expensive. That's why people also do depth averaged simulations like the Kino says, right? So, but at the same time, once we do depth averaging, then we also lose the local flow properties. So that could be a problem as well. And then after looking at the literature, we comes to question is how about LBM? So can we simulate granular flows solely based on the Lattice Boltzmann method? So in continuum simulation of granular flows, normally we treat granular flows as a viscoplastic fluid. And in this case, we need a proper rheology for the granular flow. And one of the most popular one is the so-called mu-I rheology. So we write the apparent friction of the granular flow as a function of the inertial number. And this inertial number is equal to the shear rate times the particle diameter divided by the square root of the pressure divided by the particle density. So this rheology is first derived based on very simple steady state granular flows. And then later on, Professor Lacasse, I think, who is going to give a talk very soon, proves that this rheology actually also holds for transient granular column collapses. So how to implement this mu-I rheology into a fluid solver? We have to translate this friction coefficient to the viscosity of the fluid. We know that the shear stress is equal to mu times the pressure, and it also equals to the viscosity eta times the shear rate. That's why we can write the apparent viscosity of the fluid as mu times b divided by gamma dot. And if we substitute this mu-I rheology, this expression into this equation, then we can get the expression for the fluid viscosity. And it is composed of two parts, the static part and also the dynamic part. So if we look at the static part, we will see that when the strain rate goes to 0, then the fluid viscosity becomes infinitely large. Then it can cause some stability problems in numerical simulations. That is why we need to do a regularization. So after regularization, we can plot the shear stress against the shear rate here. And you can see that the smaller the regularization parameter is, the better the approximation it will be. Now, for those who are familiar with the non-Newtonian fluid, they immediately find that this stress-strain rate relationship is very similar to the Bingham rheology, except that the line here now becomes slightly curved, and this yield stress becomes pressure dependent. And later on, you will find that the pressure dependent yield stress is actually very important to capture the granular flow behavior. We can verify our implementation by do a simulation about the granular flow down incline. And you can see that, so here we use both the Bingham rheology and the mu-I rheology. And you can see that the LBM results agrees with the analytical solution in terms of the velocity, strain rate, pressure, and the stress distributions. So to simulate granular column collapse, we also need a free surface model to capture the dynamic evolution of the free surface. And in this case, we divide the fluid cells into 3 different types. So we have the fluid cell, we have the interface cell, and also we have the gas cell. So once the calculation reaches the interface cell, we need to recover the missing density distribution functions, so which we need in the LBM calculations based on the boundary conditions we have for the interface. And actually, we also need to reconstruct the density distribution functions along the surface normal. So that means the direction has angle which is smaller than 90 degrees with this normal direction. And then the normal collision step can be done. And after that, we can treat the next fluid cell. So the advantage of this free surface model is that the gas cells, they are never accessed in the calculation. So we also call it a single phase free surface model, and it becomes very, very efficient. So to verify this model, we can do a dam break of a water column, and then we compare the snapshots from the numerical simulations and experiments. And you can see that actually this model works very well to capture the free surface. And once the rheology and the free surface model are ready, then we can do a simulation about the granular column collapse using LBM. And here we also try to do a DEM simulation as well, and we take the DEM result as a reference. And you can see that when the Bingham rheology is used, then you can see there is the unyielded corner at the early stage of the collapse, and later during the collapse, you have this plug flow behavior, which is very different from the DEM results. Well, if we change to the mu-I rheology, then a much closer match between DEM and LBM can be achieved. Although if we look closer to the DEM results, we can still spot some small differences. For example, the initiation seems to be faster in the LBM calculation. Like for example, at t equal to 0.05 seconds, we already have some materials moving down at a very back of the flow, but in DEM simulations, the particles, they still stay like quite static. And also close to the deposition, we also observe a larger area close to the upper slope. It's a flowing region, it's larger. But for the LBM results, the flowing region becomes smaller. Although I think we can further tune the parameters in LBM so that we can get a better match with the DEM result, but I think this is not the purpose of our study. Yeah. Um, one advantage of LBM is the calculation is super fast. So to demonstrate this point, we try to do a simulation using Basilisk, which is an open source software, and it solves the Navier-Stokes equations, and also it also has a module for the VOF to capture the dynamic free surface. So our LBM is written in Python and accelerated by Numba, which is a just-in-time compiler. And Basilisk, it is written in C. Okay. So the test platform is very simple. We have a 10th gen Intel Core i5 CPU, and the simulations are run on WSL2. So the default configuration in Basilisk is we need to construct a square simulation domain, and we try to establish the same simulation domain in LBM. And then in both software packages, we create a small granular column close to the left bottom corner. And then we just release the column and let it run. Oh, by the way, the result I'm going to show it still needs to be confirmed because we find the difference between the two packages is far too large. So this is the result. We try to simulate the granular column collapse using 4 different levels of resolution. So we have level 7, 8, 9, and 10. So level 7 means we have 2 to the power of 7 number of fluid cells across the domain dimension. Okay. And also keep in mind that when we try to increase the resolution, that means decreasing dx, we also decrease the time step in proportion so that the CFL condition is not altered. And here is the result for the time and the speed. And we can plot the computing time against the resolution, and you can see that the LBM calculation is much, much faster than Basilisk. Again, it still needs to be confirmed. But this computing time is not a fair comparison because in Basilisk, it uses a VOF approach. That means it also solves the motion of the air here. But in LBM, we use a single phase free surface model. That means this white space is not solved. So in that case, we can try to compare the number of fluid cells that has been solved by LBM and Basilisk within 1 second. And this is the result. And we can see that once we have enough fluid cells, the calculation speed of LBM kind of like reach a steady level. So it can do calculations like 1 million fluid cells in 1 second. But in Basilisk, what we find is when the resolution increases, the convergence rate decreases quite significantly. And as a result, the calculation speed also decreases. So this is just a simple demonstration that LBM calculations can be very, very fast. Although up to now, the LBM package we developed can only solve dry granular flow problems. And in this study, I think our target is to do LBM-DEM coupled simulations, and we try to extract some rheological informations and also pore pressure informations. And then we can try to implement this rheology and the pore pressure model into LBM so that we can carry out continuum simulations with granular physics. So conclusions, in short, we try to develop a multi-scale numerical framework for granular flow simulations based on the Lattice Boltzmann method. But we have to admit that this is still at the very early stage, and we only started this very recently. There are still a lot of things we can do. For example, for the theoretical part, we can try to implement more sophisticated rheology by considering the compressibility of the granular flow and also the non-local effects. And we also have questions like whether the model can capture the influence of the ambient fluid because we know that for immersed granular flows, we may encounter different flow regimes and also the effects of the pore pressure. And can the model capture the influence of the boundary conditions? Because we know that for granular flows, the boundary condition is neither no slip nor free slip. And can the model capture other effects like the size effects, the effects of the particle size distributions? And for engineering practice, later on, can this LBM model capture the entrainment problem in large-scale geophysical flows? For the modeling part, I think currently it is 2D, but it is actually very easy to extend the LBM code to 3-dimensional simulations. And currently, we do not consider the computational efficiency quite a lot, although it is already very fast. But I think we can further improve the performance by doing parallel computing and also GPU acceleration, which can be easily done as well because LBM calculations are local. And then we also need to think about how to implement different boundary conditions. Are we going to implement these boundary conditions in a macroscopic way or in a mesoscopic way? And how to treat boundaries with different geometries. And then when we scale up our numerical model, are we going to encounter stability problems? Because in this case, maybe the flow can be very, very turbulent. And if you are interested in some of the contents in this talk, you can check the papers here. And that's all. Thank you.
Thank you very much, Gengchao. This was an excellent talk. So I think we have 5 minutes for questions and discussions. So if you want to ask questions, so please unmute yourself and go ahead and ask questions. I have a quick question for you, Gengchao. So yes. How can you tell us a little bit more about the way that you implement the free surface calculation on your LBM solver, and how does that compare with the VOF model that is implemented on Basilisk?
In VOF, I think they introduce additional parameter normally denoted by alpha that can quantify, like in a fluid cell, how much space is occupied by fluid and how much space is occupied by air. And then they solve both the fluid part and also the air part. So they kind of like have a transport equation for that. But in LBM, what we do is we totally ignore the gas cells, the air part. So the influence of the air is also ignored. And what we do is we try to, so in LBM, you know that we have these density distribution functions streaming between the fluid cells. But if we don't, the calculation don't access these gas cells, then there's no distribution functions streaming from these gas cells to the interface cells, right? That means we have to reconstruct them. And how then it involves a little bit of detail about how we reconstruct these density distribution functions. Normally, it follows a so-called non-equilibrium bounce back boundary condition in LBM. And then once we get these missing distribution functions, then we can do a normal collision step in LBM. Yeah, then the calculation is finished for this particular cell.
I see.
Yeah, So the advantage is still we don't calculate these gas cells, so the calculation can be very fast.
I see. Okay, very good, very good. I think we have a question from Miguel Angel. Go ahead, please.
Thank you, Jerry. Gengchao, congratulations on your work. Very amazing what you have achieved so far. I have a question about the hydroplanning, and I would like to know if you could explain me a bit more. So if I think of hydroplanning as in the sense of the very dramatic video of this trolley sliding, I understand that the friction coefficient reduces significantly, and that's why the truck slides. But when I see the granular front, I have troubles imagining that a particle will slide sideways with a friction coefficient near zero. But rather what I see is that you have a fluid pocket below the granular front. So that makes me wonder whether hydroplaning is the appropriate term for this process, or if maybe I'm missing something about this reduced friction on the base that not necessarily means that the particle will slide sideways, but that the propagation of the front will reach a farther distance. I don't know if the question is clear.
Can you say that again? Sorry.
Okay, so basically is how do you understand hydroplaning in a granular flow? If you could explain me a bit more of that.
Because I listened to you that you explained quite a lot, so I don't know whether I capture your questions fully. So actually now for granular flows, it's still a bit different from the picture shown here, because granular flow is a porous media. And in that case, the fluid actually can go through the granular front, right? So whether hydroplaning can occur or not, then it really depends on how fast your granular flow, your granular front moves. It moves too fast, then we can kind of like ignore the penetration of the fluid into the granular front because it takes time. And then in that case, if the particle they move too fast, and at the very beginning, your fluid in front of the granular front is unsteady, right? And in that case, there is a velocity difference. And if it does not get enough time to displace the fluid in front of the granular front, then the granular front has to be lifted up, right? Lifted up. And in that case, there will be a thin layer of pressurized layer fluid get trapped in between the granular front and the rough base. And in that case, because of the presence of this pressurized fluid, then the friction will reduce. And actually, this phenomenon can be more significant if your particle size becomes smaller. And people actually have done some experiments, and they actually use clay instead of sand. And in these experiments, actually, you can see this granular mass actually can slide on a channel for a very, very long distance. But I don't have that video here. Yeah.
Thank you.
All right. Okay. Thank you. Thank you. So I think we have run out of time for questions. Thank you very much, Gengchao, for your talk. It was very nice. I will stop recording.